This video will cover an overview of distortion measurement and spectrum analysis, the theory of operation and specifications of a spectrum analyzer, and some of its features. We will also demo intermodulation and harmonic measurements, using both a spectrum and network analyzer. Distortion is measured in terms of the products or signals produced when an active device is driven in a nonlinear mode. Nonlinear means the output power is not a linear function of the input power, so the gain is not constant with drive level. Critical measurements for small signal amplifiers include gain, S parameters, output 1 decibel compression, output third-order intercept point, harmonics, load pull, hot S22, and noise figure. The diagram illustrates the comparison between time domain measurements, which show amplitude over time, and frequency domain measurements, which show amplitude over frequency. Nonlinear gain means the gain changes with the power level. This can be tested by sweeping the frequency response at different power levels, or by holding the frequency constant and sweeping the input power. A key figure of merit is P-1 decibel, the power that reduces the apparent gain by 1 decibel. A continuous wave power sweep can measure gain versus drive, input power at P1 decibel, output power at P1 decibel, phase versus drive, and a combination of all of the above. Achieving corrected gain numbers may require an enhanced response, ER, or a two-port calibration. To find the 1 decibel compression point with markers, first add a reference marker to the linear region of the gain trace. Then, add a coupled regular marker. Use the marker search dialog to set the target to -1 and enable tracking. This marker will indicate the 1 decibel compression point, which can be coupled to other traces. Other distortion characteristics can be observed using a spectrum analyzer. The display shows various signals, including modulation, noise, and distortion products in the frequency domain. The spectrum analyzer is used to perform different types of tests, categorized as modulation, noise, and distortion measurements. These tests analyze the frequency content and characteristics of signals. The block diagram illustrates the theory of operation for a spectrum analyzer, showing the flow of the input signal through components like the RF input attenuator, preselector, mixer, IF filter, detector, and finally to the CRT display. At the mixer stage, the input signal frequency, fsig, is combined with the local oscillator frequency, FLO, to produce the intermediate frequency, IF signals. These signals include the sum and difference frequencies, FLO, fsig, and FLO plus fsig. The IF filter determines the resolution bandwidth, RBW. The input spectrum passes through the filter, and the resulting displayed signal bandwidth changes based on the filter's setting, illustrating the effect of RBW on the spectral display. Detection determines how the sampled signals within frequency bins are displayed. Positive detection shows the largest value, negative detection shows the smallest value, and sample detection displays the last value in the bin. The video filter is positioned after the detector in the analyzer's block diagram. It is characterized by its video bandwidth, which affects the smoothness and detail of the displayed signal's envelope. Other key components include the RF input attenuator for signal level control, the IF gain stage for amplifying the intermediate frequency signal, and the sweep generator that controls the local oscillator frequency sweep. This slide shows how all the components work together. The input signal is mixed with the local oscillator frequency, filtered by the IF filter, detected, and then displayed by the LCD, which is synchronized with the sweep generator. The front panel of the spectrum analyzer includes soft keys for primary functions like frequency, amplitude, and span. Control functions for resolution bandwidth, RBW, sweep time, and video bandwidth, VBW, are also present, along with the RF input and a numeric keypad. Specifications include accuracy metrics like absolute amplitude accuracy in dBm and relative amplitude accuracy in dB. Frequency accuracy is also measured, distinguishing between absolute and relative frequency errors. Resolution is determined by several factors, including resolution bandwidth, RBW, residual FM, and noise sidebands. RBW type and selectivity are key to resolving closely spaced signals. Resolution bandwidth is defined by the IF filter's 3 decibels bandwidth. The filter's shape is crucial for separating signals, and the local oscillator stability is key to preventing signals from being spread or smeared across the display. This diagram illustrates a typical test setup for distortion measurements, involving a signal generator, an amplifier, a power splitter, and a bandpass filter, with settings shown for the spectrum analyzer and signal generator. This illustration compares two signals displayed with 1 kHz and 10 kHz RBW settings. The narrower RBW provides better resolution, showing the signals more clearly separated. Filter selectivity is the ratio of the 60 decibels bandwidth to the 3 decibels bandwidth. Analog filters typically have a selectivity of 15:1, while modern digital filters offer much better selectivity, around 5:1. The better selectivity of digital filters, 5:1, compared to analog filters, 15:1, helps in resolving closely spaced signals, particularly in the presence of distortion products or noise, as illustrated in the graph. Residual FM causes the signal to be smeared across the display, impacting resolution, as illustrated in the visual representation. This effect broadens the displayed spectral line. If the sweep is too fast, the displayed signal will be uncalibrated. The graph illustrates how sweeping too quickly distorts the displayed signal shape compared to a correctly swept signal. The effective level of displayed noise is a function of the RF input attenuation. Increasing the RF input attenuation decreases the signal-to-noise ratio, impacting sensitivity. The video bandwidth, VBW, is used to smooth noise. This is critical for easier identification of low-level signals that might otherwise be hidden by the fluctuating noise floor. Sensitivity is defined as the smallest signal that can be measured. This point is reached when the signal amplitude is equal to the noise floor, often determined by the 2.2 decibels difference between signal and noise. The most influential distortion is the second and third order. This includes two-tone intermodulation and harmonic distortion, both represented graphically as signal spurs. Distortion products increase as a function of the fundamental's power. Second-order distortion increases by 2 decibels per decibel of fundamental, and third-order distortion increases by 3 decibels per decibel of fundamental. The relative amplitude distortion changes with the input power level. Distortion measurements are crucial for determining the linearity limits of devices. A key question in distortion testing is whether it is internally or externally generated. Changing the input attenuator by 10 decibels helps distinguish between analyzer-generated distortion and distortion originating from the input signal. Dynamic range for spur search depends on the closeness to the carrier. The limit is determined by the noise sidebands, often expressed in dBc per hertz, and compression or noise limitations. The actual dynamic range is the minimum of 2 factors: the maximum dynamic range calculation based on distortion and sensitivity, and the noise sidebands at the offset frequency. The measurement range can be as large as 145 decibels, combining the maximum input power of +3 dBm and the minimum noise floor of -115 dBm. Distortion limits and noise sidebands define the achievable signal-to-noise range. For modulation measurements, the zero-span feature allows time domain analysis, displaying amplitude over time, which is useful for pulsed signals. Time-gated measurements in the frequency domain use a gate to select a specific portion of the signal's time record for frequency analysis, useful for burst or pulsed RF signals. Advanced measurements like swept power or swept frequency distortion can be performed with a vector network analyzer using frequency offset mode. Dual-source VNAs also allow swept two-tone intercept TOI measurements.